In this video, we're going to talk about the area between two curves, and in particular, we're going to look at where the formula comes from. So here's the idea. Let's say you've got two functions. Y equals f of x is up here, and y equals g of x is down here. And you want the area between these two curves for x between some value. I'm going to call it x equals a. That's my y-axis over there. And x between a and some other value b. So what I'm really looking for is this area right here. Now we can use the definition of the definite integral that we found in previous sections to derive this formula, but I want to derive it differently, and because this is at the beginning of the applications of integration chapter. And applications of integration are all about finding Riemann sums to approximate things and then taking limits of Riemann sums to find integrals representing different quantities. So I want to use that derivation here just to make sure that we understand how we're coming up with all of these integrals in this chapter. If I want this area between f of x and g of x, between x equals a and x equals b, I'm going to do pretty much the same thing that I did back in Calculus 1 when I found the area under the curve, where f of x was non-negative and it was above the x-axis. We did something to approximate that area. It was a little bit of a problem. It was a little bit difficult because this function f of x is curving. If it was just a straight line, I could find that area easily, knowing what I know about areas of rectangles, areas of triangles. We would be able to put everything together pretty easily, but the fact that it's curved makes things hard. The fact that it's curved is why we need calculus. So what we did back then is what we're going to do now. We're going to take this interval where x ranges from a to b, and we're going to split it into n subintervals. So this interval can be written this way. And we're going to divide this interval into n subintervals of equal width. Now they don't have to be equal, but in Calculus 1 and Calculus 2 we tend to treat them as equal. In our class they'll be equal, and that width is going to be, because we're dividing in the x direction, we're doing this, we're going to call the width of one of those delta x. Now since this distance from here to here is given by b minus a, so if this was 10 and this was 1, the distance would be 9, right? Because I just take the 10 and subtract the 1. So the distance from here to here is this number minus this number. And I'm going to divide that into n equal pieces. So dividing that by n, each of those pieces is going to have a width or a size of delta x. So we divide this into n subintervals like this. It looks like n is 1, 2, 3, 4, 5, 6, 7 in my picture. And then on each subinterval, we're going to choose an x value. And we're going to call that x value x sub I on each interval. Now back in Calc 1 we tended to use the left endpoint of the interval, the right endpoint of the interval, or the midpoint of the interval, but actually we could use any x value we want. I'm just going to think of this as, well, it's just a representative x value for right now. So we're going to go to that x value on that interval. Let's say we're just picking that one. And then we're going to draw a rectangle. And that rectangle is going to have a length of this top function value minus the bottom function value evaluated at that x sub I. So actually I think for simplicity I'm going to pick one. I'm going to say, let's say x sub I is the right interval, or right endpoint of that subinterval. So this is delta x. And then if I go to the right endpoint of that interval, and I evaluate f, I end up right there. If I evaluate g, I end up right there. And if I draw a rectangle like that for the right subinterval, or excuse me, the right endpoint of the interval, I'm sorry, that area is an approximation of the area between f of x and g of x for the x values from here to here. Now, it's a little bit of an underestimate. We're not grabbing that area and that area. We're wrong, but it's a decent approximation. If we did the same thing for all of these, and I'm going to use the right endpoint for all of these, evaluate the function on the top and the bottom at the right endpoint, and then draw a rectangle of width delta x and height f of x sub I minus g of x sub I. It's that y value minus that y value. We're going to get something that looks like this. Yeah, this is not the perfect picture, sorry guys. So those are our rectangles. We've got 7 of them. So you're choosing an x sub I on each subinterval. And then what did we say? We said you're evaluating f of x sub I and g of x sub I. And then you're going to draw a rectangle on that subinterval. And its length is this distance minus this distance. Or so this value of y minus this value of y. If that was a 10 and that was a 2, this distance would be 8, right? Be 8 units long. So if it's this one's f of x sub I and that's g of x sub I, the length is going to be f of x sub I minus g of x sub I. That will always be non-negative because f is always above g, or possibly equal to g. And then the width is delta x for all of these. And so the area of a single rectangle, I'm going to call it the ith rectangle, is the length times width. So that's f of x sub I minus g of x sub I times delta x. Now I, remember, is just the index of what's going to be a summation. Area sub 1 is the area of the first the first rectangle. Area sub 2 is the area of the second one. Area sub 3 is the area of the third. Area sub 4 is the fourth. So area sub I is the area of the ith rectangle. So if I is 4, it's the fourth rectangle. If I is 5, it's the fifth rectangle. It doesn't really work for 3, like third rectangle, not exactly, but you get the idea. Works most of the time. So this is the area of one of them, and now if I want the total area, well, it's approximately the sum of area 1 plus area 2 plus area 3, and I'm getting lazy, I'm just going to write it as a sub something instead of area sub. And I'm going to go all the way through a sub 7 because there are 7 of them. You say, oh gosh, that's a lot of adding. Like, adding's not difficult, but still, we've got to calculate all those things and then add them. And I really don't like having to write all that down. The mathematicians who came up with this, they didn't like writing it all down either. So they said, instead of doing that, why don't we do this? I'm going to use this capital sigma. I'm going to write a sub I out front. And I is going to start at 1. So I'll put that below the sigma. And I is going to end at 7. And that's the area, approximately. Now, if you're a perfectionist, you might say, I've got a problem with this. Look at that little space. I'm not covering that. What about that? We've got an overestimate over here. You know, we've got lots of problems. This is not giving me the exact area. If you want a better approximation, do you remember what we did in Calculus 1? You just took more rectangles. So rather than n equals 7 rectangles, maybe we've got n equals 10 or n equals 20 or n equals 100. Then we're going to have a lot smaller gaps there. It's still not going to be perfect, but we're going to have a lot less error with more rectangles. And then we said at the end of Calculus 1, but what if I'm really a perfectionist? What if I'm not happy with any kind of error at all? Then I need infinitely many rectangles. So we said the area is going to be the limit, as n goes to infinity, of that sum. And n is the number of rectangles. So this is the sum of a sub 1, a sub 2, a sub 3, all the way through a sub n. N could be 7 or 10 or 200. But we want to let n, the number of rectangles, go to infinity. So we want I to go from 1 to n, and this to be a sub I. And we just saw earlier that a sub I, well, that's right here. The top function minus the bottom function, that's the length. And the width is just delta x. And this is the definition of the integral of f of x minus g of x. Delta x is going to become infinitely small, so small we call it dx instead of delta x. And these bounds for our summation have absolutely nothing to do with these bounds here. These bounds describe x values. They say, where are we going to start with our x values and where are we going to stop? To figure that out, we look at our picture. X starts at A and ends at B. I'm looking left to right. So that is the area between two curves. Sometimes you'll see me write it this way instead. This is the top y value as a function of x. This is the bottom y value as a function of x. So it's the top function minus the bottom function. But these are vertical rectangles. I'm subtracting y values. I'm subtracting the y value up here. I'm subtracting the y value down here from the y value up here. So it's the larger y value minus the smaller y value. In terms of x, that's f of x minus g of x. At a particular x sub I, and then when we take the limit, we get all the x's. So we don't need the x sub I anymore. Delta x becomes infinitely small, and now we've got an integral. Okay, so that's how you do that. Now, here's another way of looking at the same idea that does not require a Riemann sum. I just wanted to show you, just so that you'd see it at least once. This is y equals f of x, and this is y equals g of x. And I want the area between x equals a and x equals b. Can't I just take the area under f, which is this area, the area bounded by this orange line? I'm trying. It's not exactly right. So it's that area. Can't I just take that area and then subtract that one? If you said yes, then you would be right. If I want that area right here, I take the area under f, and then I subtract the purple area, the area under G, and that's going to give me that black area in between. Well, we know that if you've got two integrals and they have the exact same bounds, the integral of f minus the integral of g is the integral of f minus g. So it's a much easier way to come up with the same thing. But I wanted you to remember this Riemann sum because we're going to be using it again over and over again throughout the rest of this chapter. So if you've got two functions like this, a top function and a bottom function, or better yet, like this, a top function and a bottom function, you do bottom or top minus bottom, and you integrate from a to b. Now, it's also possible that it could go the other way, rather than having a top function and a bottom function, you might have a left function and a right function. So maybe this is x equals f of y, and this is x, or I wrote y, x equals g of y, and we want the area between y equals c and y equals d. So we want that area right there. Well, in that case, because I've got my x values going from a function to a function, and my y is going from a constant to a constant, it makes a lot more sense to draw my rectangles this way. And now the width of one of those rectangles is delta y. And watch this with the length. Be careful. What's the length of that? This is x equals 1 and this is x equals 5, and we've got this length from here to here. That horizontal distance. What's the distance? I hope you said 4. How did you find that? I hope you said you took this 5 and you subtracted this 1. So you're going to find this x value on the right, the larger one, and you're going to subtract the x value on the left. So this, if I want the area of this one rectangle, it's going to be the x value on the right minus the x value on the left. So that's f of y sub I minus g of y sub I. That should be a y. And that y sub I is just some y value that we picked on that interval. And that's the area of one of them, one rectangle. So the total area is the sum as I goes from 1 to n of all of those rectangles, and then or the areas of all of those rectangles, and then you take the limit as the number of rectangles goes to infinity, and we get this. The integral from y equals c to y equals d of f of y minus g of y dy. The order matters though. You're going to get the wrong answer, you're going to get the opposite answer if you get it backwards. You'll see me write it this way. This is x on the right minus x on the left. But because of this dy over here, this is x on the right as a function of y. That's f of y. And x on the left as a function of y. That's g of y. Okay, in the next couple of videos, we're actually going to do some examples, but I wanted to show you where those formulas came from, and I wanted to refresh your memory about Riemann sums.